Today we're going to take a look at how we can use exponential functions in order to model growth problems. Let's take a look at what exactly that means, exponential growth. Well, suppose we have something and the price increases by $5 per year. Well, it goes up by a set amount, and that gives us a linear function like you see on the screen. However, suppose the cost of something goes up by 5% per year. Anything that goes up by a percent has a graph that looks something like this. This is exponential growth. When we're working with exponential growth, and we know we have that because it has a percent in the problem, we have the formula y equals a times 1 plus r to the t. A is the initial amount, what you started with. R is the rate of growth, written as a decimal. 15%, for example, would be 0.15. 3%, 0.03. T is the number of time intervals. So if we're looking over, say, 15 years, T would be 15. In our first example, we have a diamond ring that we purchased for $500 20 years ago. The value of the ring has increased by 8% each year. We know that because it's increased by a percent, 8%, that it's going to be exponential growth. The first thing I should do is identify the variables. A, the initial amount, is $500. R, the rate of growth, is 8%, so 0.08. T, the amount of time, is 20. We're looking at 20 years. We want to write a function now, and we'll begin by writing our formula and then substituting the numbers in. I can type those right into my calculator, and I find the value of the ring today, after 20 years, is $2,330. In problem 2, we have an example involving a fish hatchery. Typically, a catfish weighs about 0.3 grams when it's hatched. During the first 6 weeks of its life, its growth is approximately exponential, and it increases about 10% each day. They want us to find the weight of the catfish at the end of 6 weeks. Well, because it increases by a percentage, 10% each day, we know that it's exponential growth. We begin by identifying our variables. The first thing we need to note is that because it grows by 10% each day, the amount of time we use also has to be in days. So 6 weeks is 42 days. Now the period in which it grows matches the time units. Please pause the video here, see if you can write and determine the variables A, R, and T, and then come back to see if you have those correct. For A, we have 0.3, the initial amount. R, the rate of growth, is 0.10, 10%. T, the amount of time, 42. That's 42 days. Now, please write down the formula and substitute those numbers in and plug them in your calculator to see what you get for an answer. Please pause the video here. We plug the numbers in. We have 0.3 times 1 plus 0.10 to the 42nd power. When I plug those into my calculator, I end up with 16.429 grams. So at the end of 6 weeks, I can expect that little catfish to weigh about 16.4 grams. Once again, notice inside the parentheses, the value is 1.10. It's greater than 1. That's a sure indicator that we have exponential growth. Our third example discusses population. Population is a great example of exponential growth. In 1990, the population of Austin, Texas, was 494,290. They found that from the United States Census, where they count all the people in all the parts of the country. During the next 10 years, the population increased by about 3% per year. Well, we know that because it's increasing by a percent, that it must be exponential. Once again, I can identify the value of my variables A, R, and T. A is 494,290, R 0.03, and T is 10. Please pause the video here and determine the population of the city in the year 2000. When we plug that in, we end up with 664,284. Now, a good question might be, why did we pick 10 for t? Well, let's take a look. We have the population in 1990, and they want to know the population in the year 2000. Between 1990 and 2000, there's a total of 10 years. That's why our t value was 10. In our final example, we have the population of the world in 1990, approximately 5.4 billion people. Between then and 1999, the population grew at a rate of approximately 1.95% annually. What's the first thing you saw? That's right, 1.95%. Because it's growing at a percentage, it's exponential growth. They want us to write a function and estimate the population in the year 1999. Please find the values for the variables a, r, and t, pause the video, and come on back and check once you've done that. For a, we have 5.4. R, we have 0.0195. That's 1.95%. T, the amount of time, is 9, because from 1990 to 1999, there were 9 years. Now, please write the formula, substitute the numbers in, and estimate the population in the year 1999. Then come on back, we'll see how you do. When I substitute those in, I end up with 6.425 billion as my population. The final question that's asked is, if this trend continues, in what year will the population be 8 billion? Well, this is a little strange because we don't know the number of years, but we know the ending amount. We know that y, the amount we have at the end, is going to be 8 billion. We know that a, the initial amount, is 5.4. We know that r, the rate of growth, is 1.95%, so 0.0195. So how do we deal with this? Well, we simply plug the numbers in. And now I have to solve for my exponent. There are ways to do this algebraically. Those are topics you'll learn in Algebra 2. So the method we're going to use today is actually a graphing method. We'll take the left-hand side of the equation, 8, and we'll put it into our calculator as our first function, simply 8. We'll take the right-hand side, 5.4, times 1 plus 0.0195 to the x, and we'll plug that in as a second function. I'll zoom so that I can see the graphs, and I'll have something that looks like this. Now, all I have to do is find the intersection of those two graphs, and that will tell me exactly what I have. Notice it says 20.4, 8. That means in 20.4 years, the population will be 8 billion. So in 20.4 years, we're in 1990, we're adding 20.4, it'll be in the year 2010. Now, don't worry if you're not sure how to do this on the graphing calculator yet. In class, we'll take a look at this, and I'll show you so you feel a little bit more comfortable. So here's what you need to know. The formula for exponential growth is given by y equals a times 1 plus r to the t. A is the amount you start with, r is the rate of growth written as a decimal, and t is the number of time intervals that have passed. Anytime we see something that's growing at a percentage rate, then we know it's exponential growth. The graph of an exponential function looks like these two right down here. The one on the right-hand side is what we typically think of when we think of growth. But if we add a negative coefficient to the front, it simply reflects it over the axis, and we have a graph that looks like the one on the left. This is everything you need to know about modeling exponential growth using exponential functions.